All right, everybody, hello and welcome back. Today what we're going to do is we're going to talk a little bit more about I. Eventually we're going to do some operations on imaginary or complex numbers that's going to require us to have a little bit of a deeper knowledge of how we can simplify values of I. So today that's what we're going to take a look at, and then we're going to talk about the length of complex numbers. So before we dive into the different powers of I, let's remember that I squared is equal to -1, and therefore I itself is equal to the square root of -1. Now, if we are simplifying here different powers of I wouldn't necessarily say that this is more simplified than I itself. So we're going to keep that in mind. We know that I to the first power is just going to be itself. That's about as simple as it can get. Again, I don't think the square root of -1 is any more simplified. Anything to the 0 power should be 1, right? Mathematically, we know that that's supposed to be true. We did just figure out that I squared, by its definition at the top here, is -1. And now we're going to get into some larger powers of I. So for example, we have I to the third power, which is really I times I times I. All right, now using what we already know, 2 i's together is I squared, which we know from before is -1. So essentially this is going to be equal to -1 times I, or -I. I'm going to continue a similar process here. I to the fourth is I times I times I times I. Well, again, if we group them in 2's, we get I to the second times I to the second, and we know I to the second is -1. So we get -1 times -1, which is 1. So I to the fourth power is going to simplify to 1. Let's keep that process going here. Now, we can start to break it up even easier and do I times I times I times I times I. And we just found out that I to the fourth power is 1. So I can rewrite this section as 1 times I, which is just I. So I to the fifth power simplifies to I. So we've got some values here. We've done the first 5 powers. I to the 0 power is 1. I to the first power is I. I to the second power is -1. I to the third is -I. Then I to the fourth is 1. I to the fifth is I. Let's see what I to the sixth is going to be. All right, well, we've got several groups of 2 we can focus on, if that makes it easier. There's 1, 2, 3, and the reason I chose that is because we know that I squared is -1. So we have -1 times -1 times -1, or -1. Next, we have I times I times I times I times I times I times I. 1, 2, 3, 4, 5, 6, 7. Perfect. Okay? So using what we just did, we know that I to the sixth is -1. So we get -1 times I, which is -I. And then we have I to the eighth, which is I'm running out of room a little bit here, so I'm going to move it down. I times I, 3, 4, 5, 6, 7, 8. So we've got some groups of 2. There's 1, there's 2, there's 3, there's 4. I squared, which is what each of these groupings is going to simplify to, is equivalent to -1. So we have -1 times -1 times -1 times -1, which will simplify to 1. So we have now done the first 8 powers of I. If you notice, our values go from 1 to I to the first to -1 to -I. 1, I to the first, negative 1, negative I. 1. Our assumption here should be that I to the 9th should follow the same pattern. Again, the pattern is 1, I, negative 1, negative I. 1, I, negative 1, negative I. 1, I to the 10th would be negative 1. I to the 11th would be negative I, and then I to the 12th is 1. So the idea here that hopefully we're able to kind of pick up on is every time we have multiples of 4 as our exponent, there's 0, 4, and 8, the I value is going to simplify to 1. And now the reason that this is if we think about what the graph of complex numbers look like, and we zoom in very, very closely. So we've got 1, here's our real number line, and then our imaginary number line. When we have different powers of I, what we're really doing is by multiplying by another power, you are causing a 90-degree rotation. So we go from 1, 90 degrees rotated, to I, 90-degree rotation, to negative 1, to negative I, to 1, to I, to negative 1, to negative I. 1, I, negative 1, negative I. 1, and it just kind of circulates all the way around. So every multiple of 4 is going to bring us in a full circle back to 1. Let's take a look at a few examples. We have I to the 90th power. So we could sit here, we could draw our circle and go, okay, 1, 2, 3, 4, 5, 6, 7, all the way to 90. However, obviously it's not very efficient. So instead what we can do, and some of you may have figured this out already, is we can take 90 and divide it by 4. We get 22.5. The reason I chose 4 is, remember, every 4th power of I means we are rotating in a full circle around our graph. So starting at 1, we're rotating all the way around every 4 powers of I. So what this tells us is we go 22 full trips around and then half of the way around. So if we come back up here, 22 full trips around, and then half of a trip, which ends us right here at negative 1. And that's how all of these are going to go. We have 112. Well, 112, this should be over here. 112 divided by 4, well, that looks like it's going to go in evenly. So 112 divided by 4 is 28. So what that means is starting at 1, and the reason we start here, remember this is I to the 0 power, we are going to end up taking 28 full trips around. So 28 trips all the way around our circle and ending up right back where we started, which is at 1. So that means that I to the 112th power is 1. If we do I to the 167th power, well, 167 divided by 4 is 41.75. So go back to our little graph up here. We have our starting position. We are now going to go 41 times around. So it's 1, 2, and again, we're really going from 1 to I to negative 1 to negative I to 1. That's one trip around. 2, 3, 4, 5, 41 times. But then we're going to go 0.75 of the way around, which ends us right here. It's 3/4 of the circle, which ends us at negative I. So that means I to the 167th power is going to simplify to negative I. And that's essentially how all of these are going to work. Now you might want to say, okay, well, why are we doing this? Why does it matter? Eventually what we're going to do is we're going to do some more operations on imaginary and complex numbers. That's going to require us to simplify I to different powers. We're kind of setting the stage now, and we're really just building a familiarity with imaginary numbers, specifically with the value of I. Okay? So the powers of I are just going to cycle between 1I, -1, and -I. Then the pattern repeats. 1I, -1, -I. 1I, -1, -I. And we'll just continue to circle around because, again, multiplying by R causes a 90-degree rotation. Every time we are multiplying by I, we get a 90-degree rotation. Okay? Now, the next thing I want to talk to you about is something we call the size of complex numbers. Now, sometimes you will see modulus, sometimes you will see length. All of these things mean size. And in my opinion, length might be the easiest for us to understand the first time we're trying to determine the size of a complex number. So I've got a graph here so we can plot the values, the complex values, complex numbers. We have our real number line on our horizontal axes and our imaginary number line on our vertical axes. Let's say I want to plot 3 minus 2i. So I'm going to go 3 to the right on my positive axis and then down 2 on my imaginary. So I'm going to end right about there. And this is my complex number, 3 minus 2i. Now, if I want to find the modulus or the size or the length, what we need to think about is where this complex number came from. Well, what we did is we went 1, 2, 3 to the right, and then we went 1, 2 down. If I were to trace the same steps, we go 1, 2, 3 to the right, down 2, and that is how we draw our complex number. Well, if you think about what we just made is a triangle. What do we know how to do to help us find the missing side of a right triangle? Well, we have Pythagorean theorem. So in this example here, what I would do is a squared plus b squared is going to equal c squared. So one length plus my other length equals my hypotenuse length squared. So we'll end up with 9 plus 4 equals c squared, or 13 equals c squared. In order to get the value of c, I need to take the square root of both sides. So typically when we're solving and we take the square root, we're going to need a plus and a minus, but we don't really need a minus here because we can't have a negative length. So therefore, although technically we are moving down 2 here for our b value, if you will, it's going to evaluate to a positive number. So the hypotenuse length here is going to be the square root of 13, which tells us that the length of this complex number is going to be the square root of 13. All right, and that's how all these problems are going to work. If we jump down to, let's do another more similar example. If we're doing this one here, 2 plus I, we go back up here. What we're going to end up doing is we are going 1, 2 to the right and up 1. So we are going to right about here. If you think about the triangle that we just made, we are going 2 to the right, up 1, and creating this right triangle. So we have a squared plus b squared should equal our hypotenuse squared. We can make a squared our 2 squared, then b will be our 1 squared should equal c squared, 4 plus 1 equals c squared, and 5 equals c squared. In order to find that hypotenuse length, again, we're going to take the square root of both sides. So we have the square root of 5 is equal to c, and that is the length of our complex number, 2 plus I. All right, so it really is that simple. all we're doing is we are essentially creating a triangle with our complex number, right? We have our horizontal component and then our vertical component, and using Pythagorean theorem to find its length. Now, we can even do it with values like this, where we do not have a real part to the complex number. Because, I mean, technically we do, it is 0. So if we picture what our value is going to look like, we're not moving left to right. Instead, we are just moving up 7. So we don't really create a triangle, but Pythagorean theorem should be able to help us out. Our horizontal component is 0 squared, plus our vertical component, which is 7 squared, should equal the length squared. So we get 0 squared, which is just 0, plus 49 equals c squared. 49 is equal to c squared, and square root of both sides to give us 7 is equal to c. So the length of this complex number is 7, which should make sense because we're not moving left and right. We're just going up 7 values, 7 spaces. So the length should be 7. Okay? So that is all we are going to be doing for the day. Again, we're just simplifying different powers of I, which rotate between 4 different ones. And then we work on the size, modulus, or length of complex numbers by plotting them on a coordinate plane, or a plane, excuse me, and using Pythagorean theorem to determine their length. Okay? As always, thank you for listening. If you have any questions or concerns, please feel free to reach out.